Module 10. Lecture B, Building and Testing. By the end of this lecture, you will be able to implement the planned project using Python features learned in the course, test the project with different inputs to verify correct behavior and find bugs, and refine the project by improving messages, handling errors, and cleaning up code structure. Stepwise project coding. Incremental code building. When you start coding a project, work in small, manageable steps instead of trying to build everything at once. Begin with the simplest version of a feature, get it working, and then gradually add more complexity. For example, you might first handle a single expense in a budgeting tool, and only later add support for multiple expenses, categories, and reports. This step-by-step approach, similar to professional development practices, reduces mental overload, makes errors easier to find, and helps you clearly see your progress as the project grows. When using incremental building, connect each coding step to a clear, testable behavior. Instead of trying to complete the whole project at once, set small goals such as handling user input or performing a single calculation. For example, in a quiz app, you might first show one question and check the answer. Then later add more questions, scoring, feedback, and saving results. Each step builds on a working version of the program, so you can pause, adjust, and refine the design at any time. This approach keeps your work organized and gives you regular checkpoints to review your progress. Building code incrementally helps you see how different parts of your project fit together and encourages cleaner, more reusable components. As you add features, decide whether they belong in their own function, whether they can reuse existing logic, and how they interact with what you already have. For instance, you might first handle recording a single workout, then pull that logic into a reusable piece, and later add validation, summaries, and exporting. By refining the program step by step, instead of writing one large script, you end up with a more organized, reliable, and maintainable codebase. Python code, incremental code building. We will demonstrate how to build a project incrementally using a tiny quiz application. We begin with a single question, then gradually add new features step by step. After each change, we run the program and show clear printed messages so you can see the progress at every stage of development. This line explains that the script does not need any external libraries because it uses only Python's built-in features. As a result, you do not have to install extra packages. This makes the code easy to run and accessible to anyone with a standard Python installation. We define a simple quiz function that asks one fixed question: what is 2 plus 2? The correct answer is set to the word 4, and we simulate a user response that is also 4. The function compares the user's answer with the correct one, and, if they match, it reports that a correct answer was recorded. If they do not match, it reports that an incorrect answer was recorded. This illustrates the basic structure of checking a quiz response against a stored correct answer. This quiz function handles multiple questions stored as pairs of questions and correct answers in a list. It starts by setting a score of 0, then loops through each question and answer pair. For each one, It simulates the user's response by assigning the correct answer as the user's answer, then checks if they match. When they do, it increases the score by 1. At the end, it returns a message showing how many questions were answered correctly out of the total number of questions. This function checks whether a user's answer matches the correct answer in a flexible way. It first removes any extra spaces at the beginning or end of each answer and converts both to lowercase. By doing this, the comparison ignores differences in capitalization and minor spacing issues. It then compares the processed answers and returns a true or false value, indicating if they are the same. This makes the answer checking more robust and reliable. In this final quiz version, we create a list of questions, each paired with its correct answer in lowercase, and set a score starting at 0. We loop through each question and its answer, and for this example, we simulate the user always giving the correct response. A separate check answer function compares the user's response with the correct answer after trimming spaces and converting both to lowercase. Each time they match, the score increases by 1. At the end, the program returns a message that reports how many questions were answered correctly out of the total, summarizing the user's performance. The script runs 3 versions of a quiz function that gradually increase in complexity. The first version asks 1 question, checks if the user's answer is correct, and prints the result. The second version works with a list of questions, checks each answer in turn, and prints a score to show how many were correct. The final version still uses multiple questions, but introduces a separate function dedicated to checking answers, and it prints the overall score to show the user's final progress in the quiz. This material explains how a quiz application is built up step by step. It starts with a single arithmetic question and checks whether the user's answer is correct. The next version adds a list of questions and automatically keeps score as the user answers each one. Finally, a reusable answer checking function is introduced that supports case-insensitive comparison. Together, these steps show how a simple question script can grow into a more flexible quiz system with multiple questions and better answer handling. Testing early and often. Testing early and often means building testing into your coding process from the very beginning instead of waiting until everything is finished. Each time you add a new function or feature, run the program with simple inputs to confirm it behaves as expected. This helps you catch small mistakes right away before they grow into complicated problems. For example, in a reading list app, you would first test adding a single book before moving on to features like searching or sorting. By testing each step as you go, you create a solid foundation for the rest of your project. Frequent testing is most effective when you use inputs that reflect real-world usage, not just simple or ideal cases. Try typical values, unusual but still valid ones, and clearly invalid entries to see how your program responds. For example, a budgeting tool should be tested with normal expenses, stream amounts, and negative or empty values. This helps confirm the code works for common situations and reveals error patterns early, such as problems with decimals or long text. Finding these issues sooner guides your next coding steps and prevents small bugs from turning into major problems later. Testing early and often encourages you to write clear, well-structured code by breaking it into small functions that each handle a specific, predictable task. Running focus tests, such as checking how a quiz app scores a single question before testing the whole exam, makes it easier to design and reason about your test cases. As you repeatedly code and test in this way, you develop a disciplined workflow that reduces last-minute stress. Instead of facing a large, untested system at the end, you arrive with well-tested components, so integration and final checks become much simpler. Python code. Testing early and often. In this lesson, we focus on building a very small feature while testing early and often. Each time we make a small change, we immediately test it with simple, focused inputs to confirm it works as expected. By keeping the examples beginner-friendly and easy to run, you can clearly see how frequent testing helps catch issues quickly. The goal is to build confidence in your code by combining tiny steps with constant, straightforward tests. This comment explains that there is no need to run any installation commands because the example uses only standard Python features. By avoiding extra packages, the code stays simple and easy to use. The focus is on showing how to test code early and often without relying on external dependencies. We define a trip cost function that calculates how much you spend on fuel for a drive. It takes the miles you drive, how many miles your vehicle gets per gallon, and the price of each gallon. It first finds the gallons needed by dividing miles driven by miles per gallon, then multiplies that by the price per gallon to get the total fuel cost. The function returns this cost, rounded to 2 decimal places, so it matches standard currency formatting. To check that the trip cost function works correctly, we test it early using a realistic road trip example. We call the function with 300 miles driven, 25 miles per gallon, and a gas price of $3.50 per gallon. We then print the result with a label indicating it is the first test for a normal trip. This early test helps confirm that the function behaves as expected with typical input values and allows us to catch any problems in the development process. In this example, we test the trip cost function using a long highway drive. We call the function with 1,200 miles driven, a fuel efficiency of 30 miles per gallon, and a fuel price of $4 per gallon. The printed result shows how much the fuel will cost for this extended trip. This helps confirm that the function correctly handles larger input values and still calculates the total fuel cost accurately. The safe trip cost function computes how much a trip costs while checking that the inputs make sense. It takes the miles driven, the fuel efficiency in miles per gallon, and the fuel price in dollars per gallon. If any of these values are 0 or negative, it returns an error message instead of continuing. Otherwise, it finds how many gallons are needed by dividing miles driven by miles per gallon, then multiplies that by the fuel price to get the total cost. The result is returned, rounded to 2 decimal places for a clear, user-friendly value. We test the improved safe trip cost function using typical city driving values. The function is given 60 miles driven, a fuel efficiency of 20 miles per gallon, and a fuel price of $3.75 per gallon. This test checks whether the function correctly computes the fuel cost under normal conditions while confirming that all inputs are valid. The result is printed to the console and labeled as Test 3 Safe Valid to verify the function's behavior with these inputs. In this test, we check how the improved SafeTripCost function handles invalid input by giving it a negative number of miles driven, along with normal values for miles per gallon and fuel price. Because the miles value is negative, it represents an impossible trip distance. The function is expected to detect this invalid input and return an error message instead of a cost. This confirms that the function correctly identifies and responds to bad data, making it more robust. This line prints a summary comparing the results of two trip cost functions to show how they behave differently. The first function calculates the fuel cost for a trip of 100 miles, using 25 miles per gallon and $3.50 per gallon. But it does not check whether the inputs are valid. The second, safer function uses the same numbers but includes checks to handle invalid values. By comparing their outputs for the same input, the example highlights why input validation in the safer trip cost function is important. This script shows why it is important to test code early and often during development. It begins with a simple function that calculates the fuel cost of a trip and tests it with typical and long-distance examples. The function is then improved to detect invalid inputs, such as 0 or negative values, and return an error message instead of a cost. The updated version is tested again with both valid and invalid data to demonstrate its greater reliability. Finally, the original and improved functions are compared on the same input to highlight how iterative testing and refinement lead to more robust and correct code. Reusing course examples. When you start a new project, it is often best to reuse and adapt examples you already know instead of building everything from scratch. The patterns you have learned for handling input, processing data, using loops and conditionals, defining functions, and working with lists and dictionaries are flexible building blocks. You can reshape these structures for new tasks, such as managing a library of books in a similar way to how you stored and updated student grades. Recognizing these shared patterns helps you work faster and focus on what is unique about your current project. When reusing course examples, do not copy them exactly. Instead, adapt their structure to fit your new project. For example, you can take a menu-driven program you built before and change the options, messages, and data handling so it becomes a budgeting tool. The main idea of offering choices and triggering actions stays the same, but the details shift to match your new goal. Thinking this way turns your past programs into a flexible toolkit you can customize for tasks like tracking fitness, organizing work, or creating simple games. To reuse examples effectively, combine patterns from different course exercises into one coherent application that matches your project's complexity. You might, for example, bring together input validation from one task, file handling from another, and organized functions from a third. A project that collects survey responses, saves them, and generates reports can use these patterns for user input, file management, and data aggregation. Working this way speeds up development and helps you understand how these techniques apply in different situations, preparing you for real-world tasks like logging sensor data or handling customer inquiries. Python code, reusing course examples. In this project, you will reuse code patterns from earlier in the course to build a small, practical program. You will adapt a previous example that used a dictionary of grades and turn it into a simple book library tracker. You will also reuse a menu pattern to let the user manage books with actions to add new entries and list existing ones. This script relies only on standard Python libraries, so no installation commands are needed. This function displays a simple text menu that offers 3 choices: add a book, list books, or exit the program. It prints these options for the user and then reads the user's selection from the console. If something goes wrong while reading the input, such as an interruption, the function automatically chooses option 3 to exit. Finally, it returns the selected option so the main program can decide what to do next. This function asks the user for a book title and, if there is an input error, uses unknown title instead. It then asks for the author's name and, on error, uses unknown author. The function stores this information in a dictionary using the title as the key and the author as the value. Finally, it prints a confirmation message with the title and author to let the user know the book was added to the library. This function first checks whether the library's book collection is empty, and if so, it informs the user that there are no books and suggests adding one, then stops running. If there are books, it prints a header to indicate that the current library contents will be shown. It then goes through each entry in the collection, where each entry links a book title to its author. For every entry, it prints a clear line showing the title and the corresponding author, producing a readable list of all books in the library. The main function starts by creating an empty dictionary to store book titles and authors, then enters a loop that keeps the program running until the user chooses to exit. Inside this loop, a menu function displays options and reads the user's choice. If the user selects option 1, a function is called to add a new book to the dictionary. If they select option 2, another function lists all the stored books. Choosing option 3 prints an exit message and breaks the loop, ending the program, while any invalid input triggers a message asking for a valid choice, so errors are handled cleanly. When this script is run directly, it calls the main function, which is a common way to ensure the program's main logic only runs in that situation, and not when the script is imported into another program. This works by checking a special variable that indicates whether the script is being executed on its own. If the check is true, the main function runs and handles the core tasks for the book library. These tasks include showing the menu, adding new books, and listing the books in the library. This script is a simple book library manager that uses familiar programming patterns. When it runs, it shows a menu where you can add a book, list all books, or exit. Adding a book asks for a title and author, then stores them in a dictionary. Listing books displays everything in the library or tells you if it is empty. The program keeps looping through the menu so you can perform multiple actions until you choose to exit, reinforcing input handling, dictionary use, and menu-based navigation. Testing project inputs. Testing typical inputs. Begin testing your project with typical inputs that match what you expect most users to do. Use realistic data such as usual numbers, common text formats, and standard actions that align with your design. For example, this might be normal income and expense values in a budgeting tool, or entering a name and choosing answers in a quiz app. Walking through these everyday scenarios helps you confirm that the main features behave correctly, the user flow feels smooth, and the outputs make sense for straightforward use. To effectively test your project, imagine realistic user stories that show how someone would use it from start to finish. Picture a user opening the program, entering the expected information, and following the main path you designed, such as playing through a game or processing data in a tool. Focus on whether each step is smooth, logical, and easy to follow, and whether the final results match what a user would reasonably expect. This approach helps you evaluate the project from the user's perspective, rather than just checking individual features. When testing typical inputs, make sure you cover a range of normal cases instead of focusing on just one scenario. For example, if your project works with names, include short, long, and multi-word names. And if it uses numbers, try both small and large values within the usual range. For dates, test different months and years that users are likely to choose. This broader coverage helps verify that your core logic is robust and consistent. And it makes it easier to detect problems later when you move on to more extreme or invalid inputs. Python code. Testing typical inputs. Test the simple shopping calculator by trying typical user inputs and checking that the results match what you expect. Use normal purchase amounts and quantities to see how the program behaves in realistic situations. By printing the results for several everyday shopping scenarios, you can confirm that the calculator handles common cases correctly and produces accurate totals. Is commented line is a placeholder that suggests how to install an external library with pip, Python's package installer, if it becomes necessary. Because it is commented out, the current code does not actually install or require any external packages. Instead, it serves as a reminder or instruction for future use if new dependencies are added to the project. We define a function called calculateTotal that computes the total cost of a purchase, including tax. It takes the purchase subtotal and a tax rate given as a percentage. The tax rate is first converted to a decimal by dividing by 100, so it can be used in multiplication. The subtotal is then multiplied by 1 plus this decimal tax rate to add the tax. Finally, the function returns the total cost rounded to 2 decimal places, so it is suitable for displaying as a currency amount. We create a list of typical purchases where each item is a dictionary describing a shopping scenario with description, a subtotal in dollars, and a tax rate in percent. The first scenario is a small snack costing $4.50 with a 7.5% tax rate. The second is weekly groceries costing $68.20 with the same tax rate. The third is household supplies costing $125.99, also taxed at 7.5%. This collection of examples lets us simulate realistic shopping behavior and test our calculation function on practical data. The program starts by printing a header message to the console that tells the user it is about to test typical shopping inputs. This message sets the context for the upcoming calculations by explaining that realistic subtotals and tax rates will be used. By doing this, it organizes the output and makes it clear what kind of results the user is about to see. We go through each purchase scenario in the list one by one. For every purchase, we pull out its description, subtotal, and tax rate from the dictionary that stores its information. This setup lets us use these values in our calculations and in the output. It also ensures that each purchase scenario is processed separately and clearly. The code uses a function to compute the total cost from a given subtotal and tax rate, returning the amount that includes tax. After getting this total, it prints a single summary line. That line reports the purchase description, the subtotal, the tax rate, and the final total cost. This creates a clear, concise output that shows how the function behaves for a typical purchase. This script tests a basic shopping calculator by simulating common purchase situations. It uses a function that takes a subtotal and a tax rate, converts the tax rate from a percentage to a decimal, and computes the total cost. The total is rounded to 2 decimal places to match typical currency formatting. The script runs several predefined scenarios and prints a brief summary for each, showing the subtotal, tax rate, and final total. This helps confirm that the calculator works correctly for realistic shopping inputs. Edge and invalid inputs. After you confirm your project works with normal inputs, you should test it with edge cases and invalid data. Edge cases are unusual inputs at the limits of what your program should handle, such as extreme values or empty text. Invalid inputs are those that break the rules completely, like using letters where numbers are required, or referring to something that does not exist. By trying these kinds of inputs, you can see how your program behaves under stress and whether it fails safely instead of crashing. This kind of testing is essential because real-world data is often messy and unpredictable. When designing edge and invalid input tests, focus on the assumptions your program makes and challenge them. For example, if it processes ages, try values like 0, very large numbers, or even negative numbers. If it works with text, test empty input, a single character, or text that includes emojis. For file handling, try empty files, single-line files, and missing files. The goal is to confirm that your program responds predictably and gives clear feedback. Even when inputs are unexpected or incorrect. When testing your program with edge cases and invalid inputs, you should check both its stability and how clearly it responds. A good program detects invalid data, explains the problem to the user, and either rejects the input or falls back to a safe default. For instance, a budgeting tool should not accept a negative price, but instead ask for a valid amount. And a language app should remind users to enter an answer if they submit an empty response. By improving how your program handles these kinds of situations, you make it more reliable for real-world use, where unexpected inputs are common. Python code. Edge and invalid inputs. This material shows how a simple age checker is tested with both edge cases and invalid user inputs. It demonstrates how boundary values, such as very low or very high ages, are handled safely. It also covers how wrong input types are managed clearly so the program does not fail. The results for several test ages, including these edge and invalid examples, are printed to confirm the checker behaves as expected. This script runs using only Python's built-in standard library, so you do not need to install any extra packages. Everything required is already included when you install Python. This keeps the setup simple and avoids any external dependencies, making the code easy to run on most systems. The function first checks whether the input is a string made up only of digits, and if so, it converts that string into an integer so it can be treated as a number. If the input does not represent a valid integer, the function returns a message saying the input type is invalid and advises the user to enter whole number years. This process ensures that only proper integer values are accepted for further processing. The code checks whether the age value is less than 0, and if it is, it treats this as invalid because a real age cannot be negative. In that case, the function immediately returns a message saying the age is invalid. By doing this, any negative age input is quickly flagged as incorrect, which helps maintain the accuracy and reliability of the data being processed. The code checks whether the age entered is greater than 120 to catch values that are unrealistically high for a human. If the age is above this limit, the function returns a message saying the age is invalid. It then asks the user to enter a more realistic age. This keeps the input within a plausible human age range. The code checks whether the age is exactly 0 or 120, which are the boundary values of the valid range. If the age equals either of these limits, the function returns a message confirming that the age is at the boundary but still acceptable. This explicitly handles edge cases at the extremes of the allowed input and ensures they are treated as valid. The function returns a message confirming that the age entered is valid. It does this when the age falls within the normal range for human ages and does not hit any special boundary conditions. The message thanks the user for providing a reasonable age and indicates that the input is acceptable. The code creates a list of test inputs containing many different age values to check how well the function validates them. It includes normal ages, boundary values like 0 and 120, and clearly invalid ages such as -1 and 200. It also adds a number written as a string, a non-numeric string, and a decimal value. This mix of valid, edge case, and invalid inputs is meant to thoroughly test the function's age validation logic. The code starts by printing a header message to the console that explains what the user is about to see. It tells the user that the upcoming output shows the results of testing different age inputs. These inputs include normal cases, edge cases, and invalid values. This introduction sets the context so the user understands the purpose of the results that follow. We loop through each test input value and for each one, call the age description function with that value. The function returns a message stating whether the age input is valid or invalid. We then print a formatted line that shows both the original input and the message from the function. This process systematically checks every test case against the age validation logic and reports how each input is handled. This script tests a function that checks whether an age input is valid, covering both correct and incorrect cases. It accepts whole numbers, including digit strings that can be converted to integers, but rejects non-integer types. Ages below 0 and above 120 are treated as invalid, while 0 and 120 are allowed as boundary values. Typical ages within this range are considered valid. By running through various test inputs and printing a message for each, the script demonstrates careful input validation and clear feedback for edge cases. Tracking test problems. When you test different inputs in your project, it is important to record what you tried, what you expected, what actually happened, and whether it was correct or caused problems. Relying on memory is unreliable because you will rerun scenarios and change code, making it easy to forget which version led to which behavior. Treat this like a lab notebook for your program and write things down as soon as you see them. This clear history of tests and outcomes makes debugging easier and helps you confirm that your fixes really work. When you track issues, describe them clearly so they make sense later or to someone new. Instead of vague notes, like saying something just broke, specify what input you used and exactly what went wrong, such as a negative number giving an incorrect total. This level of detail makes it easier to reproduce the problem, whether it is a large income showing strange symbols or a blank answer causing a wrong quiz score. Carefully documenting these cases also builds a test catalog that helps ensure old bugs do not return after the code changes. As you collect test notes, they can grow into a simple but effective test suite you reuse whenever the code changes. Keep the original failing inputs and make sure they pass in future runs, especially for tricky cases like dates or special characters. Regularly rerunning and reviewing these tests helps you catch new bugs that might break existing features, which is a common problem in software development. Even without professional automated tools, consistently tracking and reusing tests gives you insight into how your program behaves, shows your progress, and increases confidence in your project's reliability. Polishing your project. Clear user messages. When polishing a project, refining user messages is essential because they form the conversation between your program and its users. Treat these messages as part of the user interface, even in text-only programs, and make them specific, concise, and written in plain language. Instead of a vague error notice, give a clear message that explains what went wrong and what the user should do next. Whether your program is a calculator, data tool, or game, clear messages improve usability and make the software feel more professional. When writing messages for your program, imagine explaining it to someone who does not know your code or technical terms. Clearly state what input you expect, its format, and why you need it. Make output messages describe exactly what the program has done and how that relates to the user's goal, rather than using vague phrases like processing complete. Use clear, descriptive labels for options and menus so users can easily understand what to do and follow each step without confusion. When refining your program's messages, focus on tone, consistency, and context. Keep the tone polite and supportive, especially when reporting errors, so users feel guided rather than blamed. Use the same terms throughout the interface, instead of switching between different words for the same thing. Make sure each message appears at the right time and clearly relates to what the user just did, such as explaining why an input is invalid and showing the correct format. This approach makes your program easier and more pleasant to use. Adding error checks. As you move from a prototype to a finished product, adding careful error checks is essential for reliability. These checks protect your program from problems like bad user input or missing files, so it does not crash or show confusing errors. Instead of assuming everything will work, anticipate what might go wrong and handle those cases gracefully. For example, if users enter ticket numbers, confirm that the value is positive and within the allowed range. This prevents failures and helps users avoid mistakes and recover more easily when issues occur. When you design a program, think carefully about the assumptions it makes at each step and decide what to do if those assumptions fail. Anytime your code relies on external data, user input, files, or network resources, there is a chance that data will be missing, wrong, or unavailable. For instance, a budgeting tool should check that a file exists and is properly formatted before reading it. And a language app should respond to unexpected input by asking the user to try again. By consistently asking whether values might be empty, out of range, or the wrong type, you can add the right error checks and keep your program stable and predictable. When your program detects an error, it should respond in a way that supports the user and fits the program's purpose. It might ask for corrected input, use a reasonable default, skip only the faulty part, or stop and clearly explain what went wrong. For instance, an app could request a new date if the one entered is invalid, or a data tool could ignore a bad record but keep processing the rest. The goal is to avoid crashes and confusion by giving clear feedback so users understand what happened and what to do next. Designing error handling with this user-focused mindset makes your project more reliable and better suited to real-world use. Python code, adding error checks. This section focuses on adding simple error checks to user input, so programs behave safely and predictably. You will see how to validate values before using them, and how this prevents crashes that can occur when input is missing, invalid, or out of range. The goal is to replace confusing failures with clear, friendly error messages that guide the user to correct their input. You will also compare how a program behaves with and without these basic validation checks to understand their impact on reliability and user experience. The line that starts with an exclamation mark is normally used in a Jupyter notebook to install a package, but here it is just a placeholder. It indicates that you do not need to install anything extra for this script. The message is simply clarifying that the code runs using only standard Python and does not depend on any external libraries beyond what is included by default. This function books tickets by taking the requested number and the current number available, then simply subtracting one from the other. It assumes the input is valid and immediately updates the remaining tickets. After that, it prints a confirmation showing how many tickets were booked and how many are left. However, it performs no safety checks, so it does not verify that the requested amount is reasonable or that enough tickets exist, which can cause errors if the input is incorrect. We create a ticket booking function that includes a basic safety check on the input. It first confirms that the requested number of tickets is an integer, since tickets must be counted as whole numbers. If the value is not an integer, the function prints an error message explaining that the ticket amount must be a whole number. It then stops running, so no further processing happens with invalid data. The code first checks whether the requested number of tickets is greater than 0. If the number is 0 or negative, it prints an error message explaining that the ticket amount must be positive. In that case, the function returns immediately so that no invalid request is processed further. This ensures that only valid positive ticket requests continue through the rest of the program. The code compares the number of requested tickets to the number available, and if the request is larger, it treats this as an invalid request. In that case, it prints an error message explaining that more tickets were requested than exist. After showing this message, the function stops running so that no further actions are taken and the ticket count is not changed. After all validation checks are passed, the program reduces the available ticket count by the number of tickets requested. This guarantees that bookings only go through when there are enough tickets left. It then displays a confirmation message that states how many tickets were successfully booked and how many are still available, giving the user clear feedback on the result of their request. In this example, we set the total number of tickets available to 5. This value represents how many tickets can be booked in total. By choosing a specific starting number, we can observe how the booking features respond when different booking requests are made. This helps us test how the system behaves under various ticket request scenarios. The code first prints a message explaining that, without any checks, the next function call would crash with a type error. This warning sets up a demonstration of why input validation is necessary. By pointing out what happens when invalid input is used in a function that has no error handling, it prepares the user to see the consequences of skipping these safeguards. In this example, we call the ticket booking function without any input checks, using the word 3 instead of a numeric value. When the function tries to subtract this string from an integer, the program raises a type error. Because the call is inside a try block, the except block catches this error and prints a message explaining that the program crashed due to a type error. This illustrates what can go wrong when input is not validated and how error handling can be used to manage such unexpected problems more gracefully. This part explains that using the validated booking function makes the program behave more safely. A message is printed to show that, with these checks in place, the program can now handle bad or unexpected input without crashing. It prepares the listener to see how the function manages errors in a controlled way. This is contrasted with the earlier version of the program, where invalid input caused it to fail. In this example, we call a ticket booking function using the word 3 as the requested number of tickets to show how it handles invalid input. Because this value is a string instead of an integer, the function first checks its type and detects that it is not a whole number. Instead of letting the program crash, it responds with a clear error message explaining that the ticket amount must be a whole number. This demonstrates how proper error handling can keep the program safe and user-friendly. This script shows why input validation is important in Python functions by comparing two ways of booking tickets. In the first version, there are no checks, so passing a non-integer value like the word 3 causes a type error and crashes the program, even though this is caught in a try-except block, just to demonstrate the problem. In the second version, the function checks the input and, when given the same invalid value, prints a clear message that the ticket amount must be a whole number. This prevents the program from crashing and gives the user helpful feedback, highlighting how validation makes programs more robust and user-friendly. Clean code comments. Thoughtful comments are essential for making code understandable and maintainable because they explain the purpose of the program, its assumptions, and how the main parts work together. Instead of repeating what each line does, comments should give the bigger picture, such as why certain design choices were made and where the key logic is. You can imagine writing for a new teammate who can read the code but needs help understanding the intent behind it. In a student project, this often means adding a short explanation at the top of the file and brief comments before complex sections to clarify your approach, like why you chose a particular data structure or how a calculation supports the user's goal. Keep code comments short, clear, and focused on what is not obvious from reading the code itself. Use them to explain tricky behavior or domain-specific rules that an outsider would not easily infer, such as how missing survey responses are handled and why certain rules are used. Avoid narrating every step of the code, since that can be as confusing as having no comments at all. Regularly review and update comments, and remove any that no longer match the code so they do not mislead future readers. Clear, focused comments help organize code by marking the boundaries between major components and explaining how they interact. They should describe each part's role, expected inputs, and outputs without repeating the internal implementation. For example, a comment might note that a function assumes dates are already validated, or that a particular business rule is applied. By setting these expectations, comments make code easier to test, reuse, and understand, especially for future developers working on the project. Python code, clean code comments. This lesson uses a tiny temperature converter project to show how to write clean, helpful comments. The focus is on comments that explain why certain choices were made, instead of restating what the code obviously does. It also compares unclear comments with improved versions, so beginners can better understand what makes a comment useful. Overall, the The goal is to teach clearer, more meaningful commenting practices in simple code. This note explains that you do not need to run any pip install commands because the script uses only features that are already built into Python. In other words, it does not depend on any external libraries. This simplifies setup, since you can run the code with a standard Python installation. Users can focus on the script itself without worrying about extra installation steps. This function converts a temperature from Fahrenheit to Celsius. It takes a single Fahrenheit value as input and applies the standard conversion formula. It does this by subtracting 32 from the Fahrenheit temperature, then multiplying the result by 5 and dividing by 9. The final result is the equivalent temperature in Celsius, which the function then returns. This function converts a temperature from Fahrenheit to Celsius. It assumes the input is an air temperature in degrees Fahrenheit. To perform the conversion, it subtracts 32 from the Fahrenheit value, multiplies the result by 5, and then divides by 9. It then returns the resulting temperature in degrees Celsius for further use. The describe conversion example function gives a brief overview of what the code is meant to do. Inside it, a print statement explains that the example compares unclear and clear comments in a simple temperature conversion task. This function is mainly there to guide readers or team members so they can quickly understand the intent behind a code. The script calls a function named describe conversion example, which prints a brief message about what the example is doing. It explains that the example compares unclear and clear comments in a simple temperature conversion scenario. By running this function, the program gives the user a high-level overview of the example's purpose. This helps prepare the user to understand why good code comments matter. We use a sample temperature of 77 degrees Fahrenheit, which represents a typical warm day. This familiar value makes the example easy to relate to. It also lets us clearly show how the temperature conversion function behaves with a realistic input. We use a poorly documented function by giving it a sample temperature in Fahrenheit so it can convert that value to Celsius. The function performs the conversion correctly, but does not explain how it works internally. The converted temperature is stored in a variable called bad result. Later, we will use this stored value to show that the function behaves correctly, even though its comments are unclear. We use a Fahrenheit to Celsius conversion function and give it a sample temperature value. The function assumes the input is in Fahrenheit and applies the standard conversion formula to find the matching Celsius temperature. It then returns the Celsius value, which is stored in a variable so it can be used or displayed later. The program prints the result of a temperature conversion performed by a function that has poor comments. It shows the converted temperature rounded to 2 decimal places. The output is labeled as bad comments result to emphasize that the example is about comment quality, not whether the function works. This demonstrates that even with unclear comments, the function still produces the correct conversion. This example prints the result of a temperature conversion function and uses rounding to 2 decimal places to keep the output clear and readable. The printed message is labeled to show that the function is well commented. The key idea is that good comments do not change how the code works, but they make it much easier to read and understand. This highlights the educational point that clear, thoughtful comments greatly improve code comprehension. This script compares two functions that both convert a temperature from Fahrenheit to Celsius using the same calculation, but differ in how well they are commented. The first function works correctly, but has unclear or missing comments, so its purpose and assumptions are harder to understand. The second function adds clear comments that state the input is an air temperature in Fahrenheit, and the output is in Celsius. When both functions are run on a sample temperature of 77 degrees Fahrenheit, they produce the same result, showing that good comments do not change what the code does. Instead, they make the code easier to read, understand, and maintain. In this lecture, you learned to implement the planned project using Python features learned in the course. Test the project with different inputs to verify correct behavior and find bugs. And refine the project by improving messages, handling errors, and cleaning up code structure. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.